So we're gonna start. Okay, well, presentation is in the local documentation. If you go to classes, input devices, week 10, and from there you see the local class, input device 1 and 2, and this is the class for today. Okay, there's 2 presentations, input devices 1 and 2, and then there's the same as in the presentations, but in the markdown in the website. Okay.
With the Zoom section?
I guess that you should have it on your calendar. I guess. Okay. So the idea for this week is that we're going to talk about sensors and input devices. It's a little bit weird how this year has been going because, especially in the academy, you guys have already done the machine. Normally you do input and output devices and then you build the machine, but now it's a little bit different. The idea for this week is that what we're going to try to do is like start to gather information from the environment in some sense, and we're going to try to digitalize that information and make use of it. So for this reason, this session is not called only inputs. It's also called sensors and data analysis, because we're going to talk about both. And you will see this particularly in the work that we do in the Smart Citizen project and in other things in sense making, is that we just don't want to have data, but we want to make use of that data in a meaningful way. Otherwise, data is just numbers and it becomes useless. Okay. So before we started, I just want to share with you a couple of links. The first one, well, the second one is just a class, but the first one is code repo in GitHub that has another seminar that I teach in another master here called MRAC in robotics that has a lot of more advanced techniques for sensors and input devices, and as well data analysis technique. It's a 4-day course that has much more advanced content, but that I'm sure that during this week you will get there as well. So, or during the course of the academy. So this is a good reference, and a lot of code and examples are going to be from here. I maintain this repo just as a place where I put a lot of examples for sensors, camera processing, data analysis, computer vision, and things like this. So just have a look at it if you want to learn a little bit more about it. What link? The link is in the presentation. Okay. So you can, well, as you know already, you are experts in Git, so you can clone it, and then anytime there are changes, or even you can contribute to it. If something doesn't work, please open an issue and help make it better. Before we get into technical stuff, I want just to give you some inspiration regarding what we call sensors and some interfaces that we may have with them. Okay. So you might have seen that lately there's a lot of hype into data analysis, machine learning, things called like sensor fusion, and basically or IoT in general, like having everything with sensors. You don't know if your Alexa is listening to you. You don't know if your smartphone is listening to you. There's million sensors, temperature, cameras, etc., etc. And one technique that we use for understanding or making better use of sensor data is called sensor fusion. We won't talk about that here today, but I just want to start a little bit of conversation regarding this. That basically tries to understand or tries to join a lot of sensor readings into one data stream, and then gather information from that. And this is, for instance, the possibilities that you can make making use of this technique. So on the right side, you have a bunch of sensor readings. There can be accelerometers, there can be electromagnetic interference, temperature, barometers, etc., etc., etc. And you log the data basically, right? So you know that each of the things that you do at home, for instance, they have a certain footprint, and that you can analyze that a posteriori, knowing that each of the sensors is going to behave in a different way. For instance, you turn on the blender and there's some buzzing noise. You turn on the tap and there's a certain noise plus some vibration. If you do this and try to understand the data as raw sensor data streams, but you combine it and try to detect things, you can go do things as this. For instance, you can detect when you're opening the tap, when you have the blender, when you turn on the oven or the coffee maker, etc. Now, this for me is very nice in technical sense, but I want to start to understand or ask you about what do you think about this type of things, besides the technical components that they have. Do you think it's what do you think?
Really interesting, I think. Because like you said, like you can now kind of have like a sense of how much energy is being produced by just like domestic, like things that we don't take into account because we like go with the regular lifestyle, and then you got all these statistics about how much energy is like going to by using a blender, for example. That gives you like inputs to kind of like understand how much energy you are using just like in the daily task.
Also, from a technical sense, you can also from a technical perspective, it doesn't only have to be at home, but here you see, for instance, that they're on a workshop, and for instance, here you could understand when the drill is being used, or when the saw is working, or when the laser cut or the vacuum is on. So you could detect some things and put some intelligence onto your workshop, for instance, right? That could help, for instance, into maintenance procedures, into prevention of accidents, prevention of etc. That's a good thing, right? But do you all agree that this is a good thing to have this sort of setup? There's no questioning about it in general? Like,
I think a lot of times it's unnecessary.
Okay. Can you justify why?
Your kitchen, like if you're running the blender, it's you making your smoothie, right? If you're turning on your oven, you don't need like Google or Amazon or anyone to know what you're doing in your home. Like, sure, I can see maybe some valuable applications in a fab lab or in a factory, whatever, but I think the ubiquity or pervasiveness of sensors everywhere, I think it has a lot of that.
Okay. Any other opinion?
Where is the data going and who is synthesizing this? Is it just us to view their level, or is it going to say like Amazon Alexa?
I don't know. And do you what's your concern about it?
I think it's in one way it's good to have like a and reporting, and just kind of having the ability to make those smart decisions based on the data from the individual side. But when you're actually like relying on like another service to capture all of this data, you're giving up a lot of the privacy.
That's really good. Also, I don't want to go much deeper into this, but even so this type of dialogue, I think it's quite interesting, especially in the evidence side, right? I think that from our perspective, we're trying to or just talk about things in a technical sense and we get amazed by them. But we have to understand that there are some things happening, and I fully agree with you guys that it can be helpful for many things. Sometimes it might be unnecessary, and sometimes, as you say, there's some platforms, some data streams that we're not aware of. And today we're going to talk about a little bit of these things, not only sensors, but we're also going to talk about how to make a sensor setup. Just reading the sensor data is not going to be only getting one number, putting into microcontroller and lighting an LED on and off. That's the first step, and we will do something with it. But when we want to make a real project, the data is going to go somewhere. Who is the owner of that somewhere? Where does that go? Is it private? Is it not private? Is it public? Is it not public? Do we have to put another computer? Do we have to waste energy on that? And we're going to talk about a little bit those concepts. Is it wired communication? Is it over-the-air communication? Is it actually necessary? What's our final purpose for this, right?
For example, this one, it's working through the electricity, no? Because it's plugged into the...
So this is plugged into a USB charger, and then there's a sensor a set of sensors that is fed through USB. But basically, it's a let's say just a PCB that has a USB connector, and that you, instead of having a cable, you just connect it directly to.
But it's not like the blender has a sensor.
No.
This is just detecting all these things
Exactly.
through the electricity.
Exactly. That we don't know, but it's not only that. Also, this sensor or this PCB is not only that. Another thing that we're going to talk about is how many computers do we need to do this? Do we just need a small microcontroller? At the end, these sensors are going to spend very little energy. We're going to be talking about less than 20 milliamps, less than 50 milliamps normally. A sensor that consumes more than that is really weird, needs a fan or needs something big. And these sensors don't look like that. There's a microcontroller in there that is going to consume a lot of energy, performing some smart tasks, or maybe they're going to send it over somewhere else, and there's going to be another computer doing something else. For instance, a Raspberry Pi. That computer, we could love that computer. It doesn't matter. It can be as lovely as a Raspberry Pi, or as hateful as I don't know, super closed MacBook Pro. Doesn't matter. But at the end, there's another computer on the setup. How do we communicate between both? What is the big computer doing? Is the big computer necessary in the setup? These type of things. I think it's also good to start them running. And we're gonna forget about them for like an hour, and then we're gonna come back to those things. But these type of ideas, keep them in mind when you design this setup. Also, because not only from the ethical sense, from the technical sense, it's also a nuisance. If you have to power two computers, all of a sudden you need an extra power supply, you need more cables, you need some external power source. You cannot run on a battery. If you need a big computer, that's not going to happen, etc., etc. Okay. Yeah, it's not the best.
Yeah, right, no?
Yeah.
Is it the projector?
Yeah. Yeah.
Okay, I'll touch that.
What else? So some more inspiration. Here, I'm just gonna skim through this one, but I just want you to also get some insights that when we talk about sensors, it doesn't necessarily need to be a sensor that we buy from a sensor manufacturer that just makes weird devices that magically create something out of the blue, but that we should we can invent other things, and we will talk with Edu a little bit later about these ideas onto how do we use physical phenomena. At the end, that's what we're going to try to digitalize somehow to represent events. Today's class is mostly about that. How do we use something that is happening in the environment? It can be us touching something to recognize, for instance, presence, or to recognize, for instance, that the water tank is full, or to recognize, for instance, that I am pinching a mobile phone, or etc., etc. Okay. In that sense, one weird application could be, for instance, to use Wi-Fi to detect Wi-Fi signals to detect whether or not there's someone behind a wall, because they reflect differently the Wi-Fi signals. So we are able to estimate, because of a series of antenna receptors that are not meant for that, how that person is moving, and we can derive their position from. That could be for purposeful things or nice things, or it could be for ethically questionable ideas, but this at the end is another way of using sensors or using physical phenomena to represent information. Okay. What else? Well, some more funny stuff. For instance, you could use sensors also, like what I tend to call 2D sensors, which is basically a camera, to control, for instance, machines, and with a very simple setup, try to make a ping pong ball juggling robot that basically keeps juggling this ball forever, let's say, with a set of cameras. At the end, this is like a little bit overkill, of course, but it goes again into this idea of not having to only use sensors that are for a specific purpose. We can also talk about cameras, and we will have a small overview of them at the end. Okay. So, I don't know why it does that. So, question for you then is, why do we need sensors after talking about all this? I think, for instance, Clement's answer before was a little bit like, well, maybe we don't need them. And that for me is a valid answer. Maybe we don't need sensors. Maybe we are overkilling in many setups, but why do we need sensors? What do you think? In the technical or holistic way, why do you need to gather information? Let's say, please. Okay, so basically they give us interesting information, let's say.
Maybe in that system as well, like people that use different devices to detect how their bodies are.
Okay. So basically, for instance, we could talk about information. We want to gather information from something. Let's say we want to know something, right? We want to know what the air quality is in here, what the temperature is, what the water pollution is, etc. Or for instance, we want to monitor something. Like, I don't know, we want to be able to control something, and that something can be a person if it's that person cannot control by their own means their blood pressure or etc., etc. So we want to be able to monitor their constants and their blood pressure, temperature, etc., so that we can act medically on them, right? Anything
like
else?
the word itself, sensor is to understand, to sense, to make sense, to understand maybe the environment, to understand people, to understand the city, to understand nature.
Okay.
It's a way to understand.
Okay. More insights.
So I think the human body has really incredible sort of distributed sensors. Say when we're walking, we don't realize, but we're like maybe our inner ear, we're perceiving what's proprioception. And when we're trying to automate human activities, or like driving, walking, whatever it may be, doing stuff with our hands have touch sensors all over, trying to replicate activity or automate activities that are usually made by humans. We need a lot of sensors for that, and sometimes we don't know how to make that.
Understanding
In what sense? Can you explain further? And is it like a sensor, like a, what type of sensor do you use for those things?
I mean, with the data, you're going to understand.
So we could say probably that those sensors are not like physical units, maybe as a PCB mounted or something else, but it's information that we gather from somewhere else, right? That can feed into our system from other sources and that make use of that data. For instance, I cannot know if a lot of people is sick because I don't have sensors on their homes, but I can know, for instance, information about how many people visit pharmacies and buy paracetamol, for instance, right? And that way I can know if a lot of people have headaches at home. That is. And that something is upon who to decide.
For example, earthquakes, no? Like alarm will sound like I don't know, a few minutes before the earthquake starts.
Okay.
That can save like lives by sensing.
Okay. And that goes back again to, so I normally, I don't know if this is like overall classification, but I try to simplify things in two buckets. I'd like to classify these type of things like sensors in two of those. Either they're used to monitor something. I want to gather information about the earthquakes, about water quality, about the environment, about whatever, or I can control something. And that control can be anything. That can be a machine, that can be a human, that can be whatever. It's not as nice as a human, but if you think about it as a, let's say, medical sense, it makes sense as well to, for instance, monitor, as Josefina was saying earlier, to monitor someone in a hospital, to help them recover because they cannot, let's say, stabilize by themselves because they are under medical complications, right? So for either option in our system of whatever we're gonna use, we're gonna have a sensor that is gonna monitor a system. It's gonna send, and from here I want to. You'll see these arrows pointing from left to right because the idea is that we're working from the perspective of the computer. We have a system that is acting on a sensor somehow, and that sensor is giving us information, okay? On the other sense, if we wanted to control something, we will have that system, we will get information from it, we will put it into a computer, actuate, it could be a machine, for instance, it could be whatever, and then we will send or feedback that information from the system again into our computer to understand what that effect was, right? But it all goes down to this idea of what we want to do at the end of the day, and this is the most important lesson from today, is that we want to convert something physical It can be the pressure level, it can be the temperature, it can be the water quality, the earthquake, etc., into something digital. So we want to make something that happens in the environment, and we want to capture it using different principles. And for those different principles are different types of sensors, and that we are able to interface with our microcontrollers that you already know how to program, and make them into something that the microcontroller can understand and we can decide upon. Okay. Sometimes this thing is not as direct as one might imagine. For instance, if we want to measure the water level of this tank, we don't measure, there's not a water level sensor in the market that works for all tanks and that gives us the water level in this type of tank and not in the other type of tank or whatever. What we do is, for instance, we measure the distance from the top of the tank to the actual surface, right? This is this idea of inferring and what we actually want to measure from a derived metric or another sensor that we use for it. In this case, for instance, the water level will be just the tank height that we know minus the sensor reading. We could also estimate, for instance, the speed of a wheel or the speed or the flywheel speed that some people here know, or we could use an encoder by using a light sensor and an LED. Whenever we see wheel or like the spokes are called in English, right? The radiuses, whenever one of those cross between the light beam of the LED into the light sensor, then we're able to see, okay, I have 4 stokes. I got however many pulses per minute. I divide it by 4 because I have 4, and then I multiply that by the wheel radius, and that's how fast I'm going. Or otherwise, I could just say, if I'm getting 4 pulses per minute, it means that I'm rotating once in the wheel. But I'm not measuring, there's no wheel speed sensor as such. What I'm measuring is pulses with a light sensor and an LED. Okay, and that simplifies, and I think that will give us a lot of confidence into making sensors that don't have to be super complex. We can try to make things that are not, let's say, I don't want to measure water pollution by blah, 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 blah. Sometimes what you can do for measuring water pollution is just put a light sensor, an LED, a light sensor, go deep, 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 and when the sensor is lost, then you just say the water is too turbid. That is already an estimation of, or a proxy of water quality, right? In that sense, I think it's very powerful to get these insights and understand that we don't always have to buy the perfect sensor, but that we can infer metrics for complex things with simple sensors, okay? Here, for instance, like, of course, sensors can be very complex and very simple. On the left-hand side, you have a mouse detector. And on the right-hand side, you have a rain detector using antennas and whatever else. Also, there can be a static. For instance, this sensor on the left is one of the ones that we developed in Smart Citizens. You can see it on this pole over there. It's a static sensor that measures air quality. And on the right-hand side, you have something that is moving, that is dynamic. And because of that, you have to adapt. On the left-hand side, you'll see that there's a power supply and there's a cable coming from the bottom. In that sense, it's going to be very easy to power. We don't need batteries, doesn't need to move. Data is static, let's say. But in this one, we have to be able to control remotely. It has to be light, there has to be a battery, power, etc. Okay. So for me, this simplest sensor is called the switch. Basically, if we look now from the perspective of the computer or sensing perspective, I want to know whether there's someone, for instance, or the switch is on or off. And I can know that because this light is on, right? It's not that I'm switching the switch or turning the switch on or off. And because of that, I am turning on the light. It's the opposite. I want to know when the switch is on or off by looking at the light. Okay, and for that I could put either a light sensor or I could put something that measures voltage somewhere in here, and I will know that there's a piece of information that is represented by a 1 or a 0. And this is the first one that we're gonna see, a digital sensor that can either be high or low. Either the lamp is on or the lamp is off, or there's a 1 or there's a 0, or it's true or false, yes or no, person or not person on top of the switch, there's a cat or a dog, or it's 5 volts or it's ground. And this might seem very stupid, but some years ago I did an installation, super simple, only with switches. That basically, where is this? So this mat in here, it was even presented in Fabra, etc. And this had only switches on the bottom, and they were made out of tinfoil with wood. And the moment you stepped on it, you had a high on a pin on the microcontroller, and then it was sent to a Raspberry Pi, and it was managing a projection and audio and whatever else. But it was just 16 switches with wires and nothing else. There was no computer vision, there was no cameras, there was no human sensors, there was no weight sensor, nothing, a switch. High or low, I want to know whether or not there's a person or not on top of that square. Depending on that, I'm gonna act and see if I play music, if I trigger some lights, if whatever.
Was like a mechanic switch?
Yeah.
Or like a sensor?
A simple mechanic switch. It was wood, foam, and tinfoil. Cable and cable. That's it. Okay. So the simplest sensor then is, from my point of view, is a switch. Okay. How do we read a switch? So to read a switch, you use the Arduino function called digital read. We already did as well in the academy, a little bit more advanced reading with registers that we're not gonna come back to that. But basically you just use digital read function and connect it to a pin of your microcontroller. Basically, this function is gonna give you either a high or a low. And the only thing that it requires is a pin, let's say the pin of the microcontroller that you're gonna read, and that's it, okay? As simple as that. Or maybe not so simple. Actually, we were talking about this a while back, and we're gonna come back to this topic again. You remember this concept of the pull-up resistors that we talked about? Yeah, can anyone remind why do we use them? Pull-up resistors when reading digital sensors? Okay, it's a partial answer. Maybe over someone, I see like a full disconnection of that area. I don't know if you're following in the screen or not. If you are, what?
If you want to probably like you're very outside.
Okay. Okay. Well, just tell me. I don't know. I don't feel that. So why do we use a pull-up resistor then?
Like floating state.
Oh my God. You know how to read. Okay. And more in particular, let's imagine again this example that we did a while back. Just gonna do it here in a corner. This is my microcontroller. This is the pin. Yeah.
What is a pull-up resistor?
It's a resistor that we use to avoid floating states. I'll explain that. I'll explain that in a second. So imagine that we have our switch. Let me move this away. Imagine that we have our switch in here. And this is ground. And whenever I press in here, I close this circuit, okay? Yeah, do we all agree till that? So here, my pin, let's say pin number 6, I read it, and whenever I press the button, I know that it's low, okay? So button press, we make a little table here, button press, we know that it's low. But what happens when the button is not pressed? And here, no te preocupes, están con las pantallas.
No, don't worry.
Okay. So here, I'm not telling you something, but I think probably you remember from one day that when we talked about it, is that when we declare a pin as an input, pin number 6, that day is very sensitive. What does it mean? In a technical sense, it means that it's on what we call a high impedance state, which if you read it here on the documentation on Arduino, when you declare a pin as an input, let me go to here. Configures, so pin mode, you already know, you just say if a pin is an input or an output, and when you configure it as an input, it makes, I don't know if it says it in here anymore, but I can show you that basically this pin becomes very sensitive to absolutely anything that is around. It can be voltage variations, it could be electromagnetic interference, it can be many things, and it's gonna oscillate a lot. So it's gonna pick up anything, absolutely anything. A dust, a little fly passing by, me touching with the finger, whatever, okay? So what happens when I don't press the button? That's the question. Oops. When I don't press the button, and this pin is open, let's say, to the air, what happens? What's the status of the pin? Can we guarantee that it is high or might be low? Anyone? Might be low as well, right? Because it's very sensitive. Maybe I touch it with my finger and it goes low. Or maybe there's a Wi-Fi antenna nearby and it goes low. So we use, answering to your question, a pull-up resistor to basically pull the line up to our voltage level. In this case, it could be 5, it could be 3.3, it could be whatever, so that we know that when the button, for instance, is not pressed, the circuit is completed through the pull-up resistor to here. And the button is not pressed, and we are high. Okay, is that clear now? Pull-up resistor or pull-down resistor, it doesn't matter. Either pulls up or pulls down. But the idea is that whenever we have a digital input, the microcontroller is going to set that pin in a technical sense in what we call a high impedance state, which means the pin is going to be oscillating if we leave it in open air. So basically we have to pull that line or that pin to something that we know. And that what we know is only either one of these two options, 5 or ground, or high or low, or 1 or 0. Okay? So that's the idea of the pull-up resistor. Yeah. If I have an example. Yeah, let me. In this one, I don't know, I don't remember. Let me see. Yeah. So I'll look at it during the break about the data sheet, and I'll answer the question regarding the pull up or pull down now. At the end, what you want is to know whether or not you are on a known state, right? In this case, on this particular case of reading a digital input that is either high or low, is going to become conditioned by what happens when I press the button. If the button, when I press it, is ground, then I want a pull up. If I press it and it goes to 5 volts, then I want to pull down, because I want to be able to differentiate both the states. And in each of the options, I want to make sure that I know what I am detecting, right? In this case, I assume that this pull-up resists this pin on the left. If there's a switch here, there's our switch, and then I have ground here. Because if I didn't have ground and this was VCC, when I press the button, I have VCC. And when I press the button, when I don't press it, I also have VCC. So I have 2 options, but I only have 1. So I have 2 possibilities and I only have 1 option. So I'm not able to discern, right? And in general, you are able to use pull-ups or pull-downs, depending on what your device is on the other side. Sometimes don't take this for granted, but we'll see networking and other communication protocols that you cannot interchange them. They say you have to use pull-up resistors on the data lines, for instance, which means I have to put a pull-up yes or yes. And the value of the pull-up, it will depend. Here, for the value of the pull-ups in this particular case, anything around 5K, 10K is going to be okay. There's going to be, of course, if you put a lower value of a resistor, it's going to go some current in here. And yeah, there's going to be some consumption, of course, because at the end of the day, you're using this resistor and you're dissipating a little bit of heat because there's a little bit of current. But the higher the value of the resistor, the lower the current is going to be. Yeah. What else? Here I explain a little bit the impedance, the high impedance state, basically the idea of picking random changes from the environment. Okay. Another problem that can happen when you press a button is this. Imagine or understand that when you are using a microcontroller, you're reading really fast. When we read the pin, if we read with a digital read on the loop of our Arduino, the button, we're reading at, I don't know, 10,000 times per second. And when you press the button, sometimes the contact is not instantaneous and there's a little bit of bouncing, meaning that the button presses and unpresses, right? So there's this concept of debouncing a button, that even if we think that the button is pressed, it's not, that there's a transition that can activate things that we don't want. And you see it in this graph where we plot high and low states and the oscillations in between when we read or when we plot the actual value of the sensor. So what we do to avoid this, what we do is we use the debouncing function in Arduino, and for this to okay. If it loads soon. But basically the idea behind this is that when we read an input, like this one, we don't read. So when we detect a transition, we don't read for a while. And we only assert that we are stable until we're being stable for a certain amount of time. Say, if I am reading here and I read again and I read again and I am oscillating, I don't assert or I don't say I am down. I only say that I'm down, and once I read 10 times that I am on the lower level. Okay? Come again?
You said the timing of when
Yeah. Yeah. Let me see if this loads is much better in this example, but yeah. Oh boy. Let me see if it's in here. Yeah, okay. So let me, do you see it better in here? No, right? Maybe if I put it in the text editor. Okay, so basically, let me eliminate a couple of things so that it's a little easier. Sorry? Yeah, so it's the idea of filtering the input of a button, because buttons are not as stable as we think, and they tend to oscillate especially during the transition, and they don't tend to be stable for a certain period of time. So the idea for doing so, or the problem is this one, basically. On the left side, we are pressing the button, and basically there's a transition time that is pressed, not pressed, and on the right side is the opposite. Yeah. Yeah. Exactly. You could use this, yeah. But what we explain is as simple as just not trying to, so only saying that I'm low if I have read for a certain period of time that I have. So here,
Cheaper to do it versus like,
Yeah.
the lines of code that you put in versus-
yeah, exactly. So in here, in the example, super quickly, let me eliminate this. What we need to do is, well, what we are doing is constantly reading the input. And basically what we do is, if what we're reading is different from what we think or the button is, for instance, we need a variable to store where the button state was previously. We can initialize that to a known state. But basically, if we know that it differs, then we start counting time, okay? If whenever I have passed a certain delay, then I read again and assert whether or not the actual reading has changed. Yeah. Then after that, I save for the next round and come back. Here, answering your question, you can adjust this in here, the bounce delay. And basically, the longer you put this, the bounce delay variable will be the longer this period of transition is. And you can just plot basically whether or not it's happening. This happens many times, for instance, when you are developing, I don't know, in your machines or etc., and you press a button and it starts triggering things too soon, or it never triggers things. It might be for this reason. So just plotting what happens when you press the button might help as well. Which basically is just a very simple trick to understand whenever there's a transition or not, and just wait a little period of time to measure it. Yeah. Is this idea more or less clear? Yep. Okay. So reading switches or reading, say what we were talking about earlier, it can also be done for reading pulses. At the end, we're reading a 0 or 5 volts or high or low, but we might want to do this on a certain amount of time. Imagine, for instance, that we want to measure the speed, the wheel speed. This is a very simplistic one, but we could use something like an encoder, which is something like this. Okay. Basically, we have a disk, a perforated disk that light can go through at certain times, a light source and a light detector, and that sends a signal like this. And we might want to count how many pulses do I have per minute or per second or per millisecond, so that I can know how fast that disk is rotating. Again, this idea of inference, I'm not measuring, there's no speed sensor for this, but what I'm measuring is I'm counting pulses because I have a light detector and a beam. Okay? So for doing that, we are still reading whether or not we have a high or a low, but we want to measure that through a certain amount of time. So for this, you can use a function called pulse in, which basically is part of the Arduino framework, quite simple to use. But you just give the pin number and whether or not you want to measure high levels or low levels, and it will give you how long have you been in high or low. Okay. This, then you can just convert this number into, I don't know, I have 30, per every rotation I have a period of time of, I am 30 times up and 20 times down, let's say. I convert that duration and I'm able to estimate, for instance, wheel speed or rotational speed of a motor, etc. Yes, simple function that might as well help many times. I've seen some people trying to code this one theory academy, and at the end of the day, it's just a while loop through a certain amount of time, but it's simpler if you use this urban framework. If you want to write it yourself, it's also okay. So that's it for buttons. Do you have? I'm gonna jump into something else now. Do you have any questions? Mm-hmm.
So, for example, regarding the sensor for the water tank,
Mm-hmm.
is that be an ultrasonic sensor, a light sensor, or how would it work?
What do you want to measure at the end?
I guess that's if the tank is full.
Sorry?
If the tank is full, let me know, say, for example.
Okay, but and if we want to, let's say, have this idea of inferring if the tank is full from a metric, we want to measure the distance, right?
Yeah.
How would you measure distance? For instance, you said already with an ultrasonic sensor.
Yeah.
Yeah, that could work. That's no problem. You might have to tweak a little bit the setup, but it will no problem.
Okay.
Basically, the ultrasonic sensor sends a burst of ultrasound through one emitter that reflects onto a surface, and then it comes back. However much time it took for it to go and come back is the distance that we estimate. I'm not going to go so much into the principles of many sensors now, because Neil covers that from my point of view in a very master's way. So he explains all the principles and everything, but that could be an option. So ultrasound, perfect. Another one is PIR, is a infrared distance sensor. It depends. PIRs, for instance, are used bathrooms when you don't want to touch the switch. There's a light detector that is a PIR sensor. It is a motion detection sensor. Okay, and basically you could use that as well to detect distance. PIRs are more expensive, but ultrasounds, let's say, for what we do is more than affordable. There's one question though, and is that water moves a little bit, right? And the surface might sometimes not be so stable. So when you send the ultrasound, it might reflect and go somewhere else.
Yeah.
So what you normally do is, like, you put, for instance, a pipe and a little piece of cork or foam that flows into the water that you know is flat. And then you measure the distance from the sensor to the cork. And then you just subtract the thickness of the cork, and that's the water level. Yeah. Okay. What else? More questions? So just so you know, I'm going to go through analog sensors now. Then we're going to talk about digital sensors, and I'll explain that later, because you will be saying, like, I already explained digital sensors, but no, stay with me. And then we'll take a break, and then we'll do an overview with Edu about different sensors in general. So we will just think it a little bit and open some data sheets and understand some basics, okay? Tomorrow, we will talk about this idea. So the idea of a sensor setup. So do we have a sensor? We have a computer. We have another computer, a Raspberry Pi, Node, board, whatever, and some data analysis techniques. So it's going to be a little bit more. I don't know if it's advanced, but it's probably this week is a little bit of a matter of time. That's it. Okay. But today we'll stay with the basics, and we will talk about digital inputs, analog inputs, digital sensors, and then we'll overview some sensors with that. Okay. Next, if you don't have any question, I go into analog values. So is okay. So, as you already know, sometimes the world is not just zeros and ones. There's more to it, and it might not be possible to just have a switch to get information from the world. Sometimes there will be what we call continuous data, right? Like data is not just discrete, the world is analog, and that because of that is beautiful, and we like it like that. We're not going to change that, we're going to try to measure it, and we're going to try to digitalize it so that we can make use of it. This means that sometimes our signals are not going to be, let's say, binary, but are going to be in a range of numbers from unknown threshold limits to whatever in a continuous way. And what we basically want is to just take snapshots of those signals at a certain period of time and be able to convert that value into something that we can make use of. This process, as complex as it sounds, is just digitalizing information, and by taking snapshots, what we're using in case of analog signals is what we already talked about, an ADC. So an analog to digital converter that basically takes a signal in a pin, in this case of an Arduino, measure it for a certain period of time, and tries to map it into a certain value. Okay? How it does it, this is what we're going to talk about. An ADC works in 2 stages. The first stage is called sampling and holding, which basically we take a snapshot and we pause it. That's the first part. Okay. We try to keep our signal steady. That is changing continuously, but we try to keep it steady with some capacitors and some whatever. And we try to keep it steady for a certain period of time, and we hold it. It's like as if we took a very quick picture. Okay. Once we have that picture, we try to quantize it, which basically says, okay, I'm going to read the value that I am holding, and I'm going to try to map it to the scale of values that I can read. For instance, if I am reading a value, a signal that I'm holding at 4 volts, and I can read from 0 to 5 volts, I'm going to be happy, and I'm going to say, okay, I have 4 out of 5 volts measured, or if I have 5 out of 5 or 0 out of 5, etc. I'm going to quantize that information, and I'm not going to leave it as that. I'm going to encode. Encoding means that we're going to convert. What is this? Exactly. We're going to convert that signal that we're receiving into a predefined set of numbers, and for that, since we're using microcontrollers, we'll use binary. That will basically fall into these different buckets of our ADC. And of course, as we talked about, depending on the resolution or the number of binary values that I can put here, better accuracy or better representation I'm going to make of our signal. But basically what we are doing is this sine wave that I have on the left. I pause it for a certain period of time, and then I say, okay, does it fall into this bucket? Yes. Then put it in that bucket and return 1, 1. Does it fall into this other bucket here? Yes. Then put it in 0, 1. That's it. That's all we do. However much numbers we get, so however much resolution we get, the better the signal is going to be represented. So if I have a lot of possibilities, then I'm going to be able to discretize better the analog signal, and I'm going to be a little bit closer to what it looks like an analog signal. At the end of the day, it's like a matter of zooming out a little bit. Of course, if I zoom in too much, at the end, this is going to be really discrete. And you see that it happens everywhere, screens and pictures, etc. But there's a trade-off. Okay, at the end, you don't need the same way you don't need 20 million megapixels picture on your phone, you don't need 20 million bits ADC for sensing some values. Okay? So basically what we're trying to do is read continuous values. For that, we will use a function called analog read. There has to be an ADC in the pin that we are using. So something that is capable of doing this process to sample and quantize. You see that it's not as simple as just taking a 1 or a 0, but there's a little bit more of using here. And of course, depending on the on the type of sensor, we will need more or less resolution. One final topic is that sometimes the signals won't fit into the possibilities that we can use on our microcontroller. For instance, we might be willing to read a signal that goes from 0 to 12 volts with a microcontroller that only has 0 to 3.3. And for that, we will use a voltage divider that I will explain in a second. Yeah. Yeah, at the end. So the microcontroller architecture could be 8 bits. And you could represent a 64 bits number with 8 bits numbers, right? So in at the end, your microcontroller, even if it only can have 8 bits as a maximum number, then you can group them. And the resolution of the ADC will be satisfied by that. Normally, C already takes care of that by defining types, int, long, floats, etc. And just it takes care of that for you. That's it. So what happens when the signal that we're trying to measure doesn't fit in our microcontroller? For instance, we're trying to measure a signal from, I don't know, 0 to 5 volts with an ESP32 that we all know now that it only measures from 0 to 3.3, right? So what happens? We need to use this circuit that is called a voltage divider. A voltage divider basically takes input signal on one side, uses a couple of resistors in series, and in the middle of the resistor, of both resistors, we take the output signal. Here, I have derived. Okay, but let's do it together in here. And you're gonna help me to do that because you already know Ohm's law. Okay, so imagine that we have a resistor imagine that we have 5 volts, and I want to know what this value is. And here I have 5,000, and here I have 2,000. Okay. Can you help me know what the output voltage is going to be? You can guide me through the process as well. 2,000 by 7,000 is 0.28. 0.285. And that is voltage. You what, sir? Okay. Okay, let's see. So someone here says that this is going to be 1.4. You guys got to the same more or less. Okay. Now you're smarter than me, so I'm not able to not try to understand how to calculate that in any setup. So what do can we derive that in more semantic way by using, for instance, this thing here? You remember this, right? This equation here. Yes, I hope. No? You remember Ohm's law? Yeah. So voltage equal current times resistance. So can you help me apply this onto this circuit? I is the current. Okay, first question. Where is the current? How is the current going?
What was the question?
The current. Here I have voltage and resistance, right?
Yeah.
But I don't know current. How is the current going in this circuit?
Voltage divided by resistance.
I mean, like, you know, let's say if I draw it here, that in a drawing sense,
It's divided into the
so where, sorry? I start here or here?
close to R1,
Goes to R1?
and then some of it goes to the out, some of it goes to R2.
Okay. Okay. That depends, because it will only go to be out if I have something here. Right? Like another resistor. Otherwise, this is an open circuit and there's no current. Let's assume that there's no circuit in there and that I only have this current. Okay? So this is I. That's current. Okay? So equation number one, can you help me apply this to V in? V in is going to be equal to?
What would it? 5 volts?
Okay, we already know that. Equal to
I times R.
I times,
R1 plus
okay, R1 plus R2. And V out equal question mark, equal, equal what else? I2, but do you guys agree with me that this current is the same for both? Do I need I2 times R2 or can I just say I? I'm asking.
The same, no?
So it's the same current, right? Okay. So let's imagine now that I divide both sides. Okay, and I say V in divided by V out is equal I divided by I, which I is 1, so it doesn't matter. And then R1 plus R2 divided by R2.
Why the out is E times R2?
Sorry? The out is I times R2. Yeah, why? So what? Let's isolate this part of the circuit. And I'm gonna put it in here. I have P out. R2. So this is voltage. And this is current. Do you agree with me that this is the same as I think we looked at it in this way. Be out and current, right? It's the same thing, no? You sure? Yep. So it applies, right? So V out is the same current as this one here is seen times the resistance, which is R2. Okay. So basically now, as you have derived, is if I divide both sides, V in divided by V out, and R1 plus R2 divided by R2, I can just refurbish this a little bit, and basically V out is equal V in times R2 divided by R1 plus R2. And if we do that, we say 5, let me clear the screen. So if we apply this, we say 2000 divided by 7000 times 5, 1.2. Good. So this means now, as you rightly guessed, that if I have a sensor that gives me 5 volts, and you will find a lot of them. For instance, there's one very common sensor here called DHT11 that gives from 0 to 5. And you very likely have built a Bartholin already that has an HP32. You will have to use a circuit like this one to be able to put that signal into the Bartholin. Otherwise, what will happen is that your reading is going to be looking like this. And here, all this part and all this part, you miss it. Okay, so basically you have to use this, which is divides voltage, nothing else, with 2 resistors. And with the equations that I showed you, well, that we derived together actually, and that are also here, you can find out what the values of those resistors are so that you can read an analog signal into a microcontroller that has lower range. Okay. What else? But basically, this is a better representation of all this. If I have no voltage divider, I might be over the range of the ADC. And with this voltage divider, I go down and get it. This is also the circuit that you will use for LDR, which is a resistor that changes with light. And with this value, you could, if you think of it, if you measure the voltage here in the middle, you are able to derive what the resistance of what value of this resistance is. And because of that, you then are able to determine how much light there is. Okay. This also applies not only for light resistance, but for a lot of the air quality sensors that we use in Smart Citizen that basically change their resistance when there's pollution here. So basically the electrical capability or the resistance of the sensor changes because there's some sort of pollutant. We measure that resistance and we know that some resistance equals to some concentration. Then by only measuring the voltage with this circuit, you are able to determine however much concentration there is in the air. Okay. So here, just some words. It's important that whenever you use an analog sensor, it's adapted for your microcontroller. Otherwise, you have to use a voltage divider. And many times it can be that your sensor measurement is not what we call centered, which is this concept. Okay, so you're measuring on the top of your ADC range, and basically you want to center it down or bring it down so that you can use the fullest length of your ADC. Actually, what you would try with this combination of resistors is not to do from this to that, but ideally, you would try to do something like this. Because then the buckets that you can put them in here, or you can use for the ADC, you use them all. I mean, I'm using all the resolution. Otherwise, if I have a signal that only fits in this lower part, then it means that all these parts I'm not using them. Okay. Any questions regarding analog sensors? Regarding this, you can use the analog read function. And here, important, already you see a table in here. That means that there's something to pay attention to. Operating voltage. Otherwise, you need a voltage divider. Here, 5 or 3.3. Okay. Usable pins or pins that have ADC. Remember that not all the pins are able to perform this operation, and you have to look at the table. Finally, here on the right side, you have a resolution, which is however many buckets you have to fill in with the signal that you're measuring. 10 bits is mediocre ADC, 12 bits is okay, 16 bits is posh, okay? 24 bits is like insane. Just think of it as a matter of, so 10 bits is 1024 buckets, 12 bits is 4,000, 16 bits 65,000, 24 16 million. So normally you will see 16 bits ADCs for spins. I'm actually, and I'm not, just so you see that I'm not telling you bullshit, and then you don't think that I am like here just talking about ADCs because I like it. But we are redesigning right now a board in Smart Citizen that has exactly that. Two 16 bits ADCs to measure air quality sensors that give us a very fine voltage from 0 to 5 volts. And that's that. That's my premise. I use these ADCs, I make my board, and I send it to my partner. The same thing that you're going to do this week. Okay. So just that you see that I'm not telling you anything that is not applicable. We do this every day. It's nothing that we're inventing here. It's all like, the analog read function, you'll see that it returns a value of the ADC related to the ADC resolution. So if it has 10 bits, the minimum number is going to be 0 and the maximum is going to be 1024. So you have to compare that. Okay. So when you get 1024, it doesn't mean that you're measuring 1024 value, volts, but 5 volts if that's the maximum reading that you can measure. Okay. Sometimes as well. Is that clear or not? Sorry. Is it clear that when you get, for instance, if I get from analog read 800 and I'm using, okay, let's do it again. Analog read. I'm giving you as data voltage range equal 5 volts. Resolution equal 10 bits. And the analog read function gives me and this gives me a value of 450. What is the voltage level? Could you help with it? So analog rate is giving me 450. I have 10 bits and 5 volts. What is the voltage level that I'm getting? Okay, so we're saying 450 divided by the resolution. So divided by 2 to the 10, and then this times 5. Yeah, okay. So this will give us 450 divided, it's 2024, right? 450 divided by 224 times 5, it's 2.2 volts. Yeah. One way I like to do these things, if you sometimes doubt if it's multiplying or not, and you don't have like technical background or whatever, it sometimes helps to know what do I want to get at the end. I want to get volts, right? And I have bits. Do I have volts somewhere else? Yeah, I have volts because of the voltage range. And then I want to eliminate bits. So I divide bits by bits. This goes away, and I have volts. Yeah. So my thinking sometimes is this is 450 bits. The resolution is 1024 bits. So this basically is nothing. This is a number, and I have 5 volts. So at the end of the day, I have volts. Yeah, just for you to see if it's multiplying or dividing.
The value for 50 is for 50 bits. 450.
450 is bits. Yeah. Well, no, it's not bits actually. It's let's call it reading.
So technically, it's like saying 450 buckets. Or 50.
Yeah, exactly.
The 1,000.
Let's say like that. Buckets. Some people also call it bins.
Yeah.
This is it. Yeah. So bins divided by bins times volts. If I divide bins by bins, then it's just a number. The units get away, and that's it. Let's put another, just a quick example, and I want someone else answering. Gonna delete, actually, I'm gonna delete this. What happens if I have a 16-bit ADC and 3.3 volts voltage range, and I am reading the same value, but no, actually, let's just keep it like that. Anyone? What is the voltage level if I have 16 bits and 3.3 voltage range?
It's 5,500, but 16 bits. Divided by 4. Otherwise, 14 divided by 16 bits.
Okay.
Times 3.3.
So that gives us
um,
150 divided to 65535 times 3.3. very little, so 0.02, which makes sense, right? We're saying that we're reading a very small value, but we have a lot. Before we were saying that we had 10 bits, and we got a value of what was it? 450. Yeah. Yeah. Yeah, so the equation would be analog read results divided by 2 to the bits times voltage. Yep. Do you feel okay if I ask you to do another one, a little bit more complicated? What happens? Yeah. What happens if this 3.3 sorry. This is a 3.3 microcontroller, an ESP32. Okay. And I have the voltage divided from before. And this voltage divider is 5,000, and this is 2,000. And here, I know that my microcontroller is up to 3.3 volts and has a resolution of 16 bits. I know I'm able to calculate now this, so I have 0.22, right? I know this number here, right? But what I want, is it that what I want ultimately, or do I want this one here? Which one do I want? This one, number 2, or number 1? You want number 1, right? Because this is your sensor at the end. This is what gives you the real information. This is just a adaptation that we're doing, right? So we could recalculate this 0.2222 and do the opposite as we did before, times 7 divided by 2, and then we would get the real value in here. Yeah. So we will do the operation, the reverse operation. That's good. Is that more or less conceptually clear? Yeah. Cool. So before we take a break, I know that you like when I say that because it's not the break time yet. We are going to have a look at one other concept, which is, well, I'm going to apologize, and then we're going to talk about digital sensors. Digital sensors are a type of sensors that we interface with them digitally, meaning that we don't read voltage levels as high or low only, a switch or pulses or whatever, but they are a sensor to which we communicate, or with which we communicate using digital protocols. Those digital protocols could be many things. Could be I2C, networking protocol we will talk about in 2 weeks. SPI, another networking protocol, could be serial, could be Modbus, Ethernet, etc., etc., etc. That's a digital sensor, meaning that we have Again, our little schematic with our system, the sensor, and the communication between our computer and our sensor happens in a digital form. And it doesn't send only a 1 or a 0, it sends a lot of them and very fast. And we call that a communication protocol, which basically establishes some standard for like I2C, SPI, etc. So sometimes you will see some boards in here that are not as simple as the ones that we've been talking about for digital sensors, and it means that these are using digital communication protocols.
There's something that we usually have information.
Yeah. So libraries for this, 2 main libraries. One is called Wire. Wire is for I2C. It's an Arduino library, a standard one for reading I2C sensors. We will see how to read them in detail in the networking week, just so you know. Or SPI. SPI is yet another protocol that you can use. If you are using this on a Raspberry Pi, you need to first enable I2C interface, etc., etc. And here, one important thing to know is that part of the processing of what we call, of what I call the heavy lifting, let's say, is the processing of the data is done by the sensor itself. And the sensor in this case has a small microcontroller inside that does some operations. Very tiny microcontroller, probably there's 10 lines of code, but that reads some sensors, or reads some voltages, calculate something, etc. But the sensor already gives you a value that is somehow calculated. This is normally the trend for all sensors nowadays. There's very little sensors that are so simple, let's say, as just an analog input or digital input. It's important that we know how to use them, but almost all the sensors are now going into this process of digitalization. And basically, you need to know a couple of things. First thing is how to interface with them, that I already told you how to do it, Wire or SPI. Second one is that we can have the same problem as we had before with the voltage levels. There might be 5 volt level sensors that we have to interface with a 3.3 sensor. And in this case, I would love to see you one day asking me for a level shifter. You use this little board, which basically is the same concept as a voltage divider, but works in both directions. Okay, and converts signals from a low voltage side to a high voltage side. You will need this to interface digital sensors, important, because otherwise you can either burn the sensor or burn the microcontroller, or it won't work. Okay, but basically they normally look like this, very tiny boards, like 2 centimeters by 1 centimeter, or not even. And they have like this shape more or less. Here you see that there's a high voltage on the right side and the low voltage. And then there's different channels. This doesn't need ground. Actually. They don't need a ground to operate. There's only high voltage and the channels. Okay. If you want details on how this is built, here in the Pololu website, there's a little description of how this works internally. But basically, it's a bunch of transistors that is able to convert low signals to high signals, acting as an amplifier. Okay, so before we take the break, again, I'm just going to give you very quick guidelines on how to choose some sensors, specifically for your application. I have, first question is, who does the heavy lifting? Meaning, and heavy lifting means who does the data processing, who provides for the energy, and who does the post-processing afterwards. Does the sensor need post-processing or not? Does the sensor need calculations in between, like this voltage level conversions? And does the sensor consume a lot of energy or not? And does our microcontroller provide for that energy or another power supply? Second thing is, well, this is just like a small visualization of that. Do we have our Arduino powering the sensor, or do we have our Raspberry Pi powering the sensor? Do we need a Raspberry Pi or another computer to analyze the data afterwards? Do we need such big thing, or do we need something smaller? Do we need an external power source and something remotely? Because, for instance, we have a robot that is moving around in the space, and we need to have a battery that powers our Arduino that needs Wi-Fi to send data over to another computer. That is all consumption. Start thinking about these things. And especially always review the data sheet. We're going to see a couple of examples with Elena about the voltage levels. First of all, because you can kill the sensor or the microcontroller. And if they are the same, good. If they are not the same, digital sensor, use a level shifter, analog sensor, use a voltage spike. Okay. And for me, I think this not only applies for sensors, but for everything. I would just suggest that you don't overkill. Try to keep it simple. For instance, what Clement said at the beginning of the class, for me it's interesting to see that you already have this point of view that sometimes the simpler the better. Look for existing solutions already, like SparkFun, Adafruit, GitHub, etc. You will find a lot of things, and then ask us. And also use libraries as well, like SPI, Wire, other libraries to interface sensors, etc. that a lot of people have developed, and that will help, let's say, in your development process. And that's it. We're gonna, if you want, take a break. If you don't have any questions, and then we come back, I don't know, 15 minutes.